So we're at lesson 4 for chapter 3, just a second day taking a look at conservation of energy, just continuing on in that note package that we've got. And again, the physics is actually the whole idea of working with this equation, knowing what we can throw away. So this question here, got a car, 1,700 kilograms, okay, that's typical, and it's going 24 meters per second, and it's just going to coast with no friction down a hill, so it's going to pick up some speed. We're going to find the speed at the bottom. So again, the whole plan is knowing what to keep and what to throw away. It sounds like we're going fast at the beginning, so I would keep the original kinetic energy. We're going to go down the hill, so we must have been up the hill at the beginning. I would keep this one. Work in. There's no elf. There's nobody running behind the car. And just because you're going, that's not a force, right? So there's nobody adding extra force. And you might think, what about gravity? Well, that's included in the potential energy term. In the end, we're at the bottom of the hill. We won't need that one. We're going to go really fast, and there's no friction, so we can throw that one away. And so this story involves only 3 terms when we actually go to do our math. Now, we've now seen both of the work terms get thrown away. All of the terms that are left have m's in them. So it was nice of them to tell us that it was a 1,700 kilogram car, and I really don't care. You can actually cancel the m's out. This is a mass independent problem. Save yourself some big numbers and just reduce this thing by dividing by mass. And then we're good to go. We can find the speed at the bottom. That's just the second velocity. At this point, there's no physics left. Okay, it's just some arithmetic. Yeah, you can get the v squared by itself and then take a square root, and you're done. You're going pretty fast, right? Over 100 kilometers an hour. 30.6 meters per second at the bottom of this hill. So the physics is all the stuff up to like about here, just knowing what to keep and what to throw away. Okay, next example, little smaller car, 1,200 kilograms, and it's going to coast up a hill. And it's a 15-degree ramp, 15-degree hill, and it comes to a stop, kind of like a runaway lane, right, after it's gone 58 meters diagonally. Okay, how fast was it going initially? There's no talk about brakes. So I'm going to be throwing away this term. It wasn't up high at the beginning, so that's going. We're looking for the original speed, so that's staying. No elf, so that's going to go. It does go up the hill. I'm going to use MGH. It's not like we're going to go higher than, Mount Everest, but I'm troubled because I don't know how high it goes. I don't know the height. I just know we go 58 meters diagonally. Okay, well I have to kind of think of the right angle triangle that's going on there, right? I've got the hypotenuse is 58, it's a 15-degree angle, and I'm looking for that opposite. That'll be the height. And then in the end, we're going to come to a stop, so that'll be gone. So a lot of these terms go away, right? Very few are left. We're just going to take some speed and convert it to some height. The m's are going to go now because everything that's left has an m in it, right? The 2 terms that are left. The h. The reason why I've got this example here, if somebody gives you, let me just put the answer fully up. If somebody gives you a picture and they say, yeah, okay, look, we're going to go, in terms of a diagonal, we're going to go like this, 58 meters with a 15-degree angle, then it's going to be important for us to know this right there. What's that height? Well, we can just do a little right angle trigonometry, and that's where the 58 sine of 15 comes from. Okay, so yeah, sometimes you'll have to go and do a calculation or two to find one of the numbers that'll work nicely for us. Okay, but I like the idea that we could cancel the m's, and we can only do that because both work terms were gone in this story. There was no friction and there was no elf running behind the car pushing. This next one, 75 kilogram box is being pushed with an applied force of 200 newtons across a level floor that has some stickiness, right? So there's going to be some friction force there. We're going to go for a distance of 4.8 meters. Got an initial speed, and we're looking for a final speed. Okay. Well, just so you know, as a physicist, when I look at this story and I see all this talk about forces and then distances, I know I could go and do exactly what we did in chapter 1. I could go and draw myself my free body diagram, right? I've got my weight, got my normal force from the floor that happens to equal the weight, got the person pushing, 200 newtons. I could go and find this friction force. I could find the net force. I could find the acceleration, and I could do kinematics, and I could absolutely find the VF. It totally works. This way is just faster. So if you notice there's talk about forces and distances, then consider using conservation of energy, because we have an ability with these work terms to put in forces and distances. And that's what I'm going to do here. So MGHs, no, I don't need them. It looks like it's a level floor. There's no hills, no gain or loss in height. We do start with an initial speed, so we should keep that one. Definitely got a person, pushing in there. There's going to be some friction, and I'm looking for that final speed. So some of this stuff can go. I can throw away the potential energy terms, but the rest is going to stay. And ultimately, we're looking for that second velocity. Okay, plug and play. This is classic conservation of energy. Big, long-looking equations that actually only have one thing missing in them. So I've got my 1/2 mv squared at the beginning, got my person pushing, right, this elf pushing along, and then in the end, there's my final speed, and then, there's some heat. Okay, so there's the thermal energy that goes into the ground as we warm the ground up. And I'm calculating the force of friction, mu mg. I'm not on a ramp, right? So mu mg is fine. And then the distance. One thing missing, take a square root, story's over. You're going to be going a little over 3 meters per second. Okay, the next one. Actually, the next two kind of come as a pair. Got a 50 kilogram skier. They've got an initial speed there of 6 meters per second, and they're going to go diagonally down this 30-degree slope. Okay, so there's that same thing again, right? Got the diagonal distance with the angle, so we should be able to find a height for that. There's a little bit of stickiness with their skis, and we're going to find their final velocity, how fast they're going in the end. Okay, got my big giant organizing equation, and here's what I can throw away. I have no elf running behind them pushing, and in the end, they're going to be down at the bottom of the hill, so they won't have any more height left. But they're going to start off up high, and they're going to start off with some speed, and I'm going to see how fast they can get going to at the bottom. But there is going to be a little bit of heat created as well. 40 meters is not higher than Mount Everest, so an MGH would be just fine. At first glance, I would say don't cancel the M's, because I don't see an M in this algebra here, at least not yet. But then with a little bit more work, it might show up. Just like the example with the car on the hill, here is the way that we can find the height. It's the same triangle, right? Just going downhill instead of up. The D is the hypotenuse, and then this will allow us to find the opposite, which would be that vertical change. Okay, going to go mu times Fn, and for a skier on a ramp, the Fn won't equal mg, but it'll actually be mg cos theta. So I've got mu times my Fn, there's my force of friction, and then times the distance. Oh, hey, this is interesting. There's now a mass everywhere, in every single term. So we don't even need to know that they're 50 kilograms. We can actually toss the mass. And then the calculation goes pretty nicely. Big, long equation, but there's only one thing missing, just the speed. This is that right angle triangle right of the hill. And I guess it looks kind of like this. There's our hill. It's 40 meters, 30-degree angle, and then we're looking for this. What's that vertical change, right? So that's the 40 sine 30, 20 meters actually. And then this big long deal over here is us finding out that thermal energy, that heat, force of friction multiplied by distance. 19 is the answer, or really, really close to 19. Rounding, we're going to hit 19, and then this leads right into the next example. So they've come down the hill, they've reached the bottom, they've increased their speed from 6 all the way up to 19 meters per second, and now they're going to hit just some flat snow, and they're going to coast. So it says, how far will they travel on level ground? Starting off with the same 19. So what can we throw away? This is the physics right here, looking at this, deciding what to throw away, what to keep. EPI, are they up high on a hill? Well, not for this part of the story. They're already down. Are they going fast at the beginning of the story? Sure are, right around 19 meters per second. Work in. Is there an elf running behind them? No, nobody's pushing them. EPF, do they go up a hill? Nope. EKF, are they going fast at the end? Nope, they're going to ski until they stop. Work out, Was there any rubbing, any friction, any heat? Yeah, with the snow. So everything goes except those two terms. And we're down to just this. Just like the last one, at first glance, I would say, oh, don't cancel the m's. It's not mass independent. But then when you start to think about it a little bit more, that friction force for the skier would be mu times Fn. On the previous example, we had to do mg cos theta to find the Fn. Here now, mg will be just fine when we're on level ground. It's an angle of 0, right? Cosine of 0 is 1. So what was mg cos theta just turns back into a nice, like physics 11-ish mg for the Fn. Now it is mass independent, so now you can throw the m's out and we'll plug and play. The number wasn't exactly 19 in the last example, so I like to try to be precise and go and grab the best I can, and it was just a little under 19, 18.976. Probably wouldn't make any difference, but I like to grab as many digits as I can when possible. So it looks like they're going to go a couple of football field lengths here, 183 meters before they come to a stop. Getting down to the last couple of examples. This one shows a changing force that's applied to an arrow that's shot from a bow, and we're going to shoot the arrow straight up, and we're wondering how high will it go. So this is kind of a double conservation of energy. The bow will actually do some work on the arrow and make it go really fast when it leaves. So we'll do work to get speed. But then instantly, we're going to see that change into another story where the speed is converted into height. We can skip the whole speed part, and we can say, you know, at the beginning of the story, there's a bow there that's going to do a lot of work, and at the end of the story, there's this arrow dangerously up high in the air. And so we'll just skip the whole speed part entirely. So as I look at this equation, I'm going to start on the ground, no EPI. I'm going to start with the arrow in the bow, not moving, so that's 0. The force, varying as it is, will do some work. No problem. I have a plan for forces that change. It just involves finding area. In the end, we're going to go up very high. In the end, if you wait long enough, right, it'll go from a push to a speed to a height. In the end, there will be no speed. And there's no talk about any air friction, so I'm just going to leave that term out. And we're going to end up with just this. So all we have to do is find the work done by this bow, and then say, yeah, ultimately that's going to make the 40-gram arrow go very high. But the work in is just the area underneath that graph. That's my plan, my strategy for that left-hand side. Just what's that area? Just going to go base times height divided by 2. And then my right-hand side will be my MGH. It's not going to go higher than mountains, so I think MGH will be fine. So 1/2 the base times the height. That's what's going on over here. This is just me finding that purple area, right? Because if I can find the area under that graph, I have found exactly how much work there is. And then here's my MGH. Plug and play, it's done. Did have to change the 40 grams to 0.04 kilograms. It goes pretty high, like a football field and a half up. And that's going to take us to our final example, I believe. Got a meteor heading straight for the moon. I'm liking the story involving the moon because there's no air on the moon, so there's no air friction to worry about. The meteor speed is really fast, 2,000 meters per second, when it's 5×10 to the 6th from the moon center, and we're looking for impact speed. That's higher than mountains, so MGH will not work. But we can use our more exotic version, that negative g mm over r. So there's my kind of base equation, helps me get organized, and I can start thinking about potential energies. I am going to use that negative g mm over r, so I will have EPs twice. Nowhere in this story is the meteor infinitely far from the moon, so those EPs both before and after have to be there. There's no ELF running behind the meteor, shoving it at the moon, so the work in goes. And the moon has no air, so there's no air friction, there's no heat, there's no loss there, which is great. Just those 4 terms, and so that's going to look like this. And once again, it's worth saying another time, you do need these twice, even though in the end it does crash into the moon. This final one here will not be 0, because we'll still be 1 moon's radius away from its center, and there's still going to be a value there. And so I just went to my formula sheet to go and grab that moon's radius number and the moon's mass. I did cancel out the mass of the meteor It doesn't matter at all, and it occurs in every single term. So it's gone. And then I'm left with this. Once again, one big, long, ugly-looking equation, but it's only got one thing missing, just the final speed. It's quadratic, so you get the v squared by itself and take a square root. This 1.74 number, just the moon's radius, right off the formula sheet, and the 735 is the moon's mass, right off the formula sheet. And we're done. This thing ends up going almost another kilometer per second, gets up to 2.77 kilometers per second by the time it's going to impact the moon. Key thing on this one, like the key takeaways, forget the number in the end, that's not important. Key takeaways, we could not use MGH because it was such a big elevation change. And since we're using the negative GMM over R instead of MGH, you have to put it in twice. It's going to be on both sides of the equation. And that wraps up our conservation of energy review for a couple of days.